ठीक है। आ रहा है सर? आ रहा है ना सर? नहीं नहीं, ये तो आना चाहिए S3। ये हाँ, वो थोड़ा टाइम लगेगा। नहीं, वो पुराना है सर, मैं अभी भेजता हूँ ये। ठीक है, चल ही रहा है। मैं आपको ये वाला लिंक अभी भेज रहा हूँ सर, ये है फाइनल लिंक। वो कुछ गड़बड़ था।
सही से कटिंग करके अगर से पीछे
आ रहा है ना सर? अभी आ रहा है ना सर? अब आ रहा है सर इसमें? कैप्चर क्यों कर रहा है?
ज़्यादा वाली तो इनको बन सकता है। चलो सर, अब तो क्या सेटिंग पासवर्ड पे सो जाए करेंगे।
I think Zoom is programmed.
ठीक है सर, मैं नीचे जाता हूँ, अभी कुछ काम
चालू है क्या? बंद जब सर्विस चल रहा है ना, तो एक ही बात में हम लोग नहीं पड़े तो चला लेते हैं आज का चालू करना मान करवा के सब कुछ दिख प्रोग्राम को किया अपन सुनी करते हैं पूरा बंद करना लगता है किसको उसके सर के सामने उसके हवा के पास बैठना है
मैंने बोला जो चलना है तो ये क्या 7% ही है क्या?
अरे सर उसको छोड़ो वो वर्तमान सर उसको प्रेजेंटेशन
कहाँ है पता नहीं दिया नहीं ना ये इसको म्यूट करो भाई।
हाँ मैं बोल रहा था कि आवाज यहाँ
बैग में रख दिए।
हेलो 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 दोनों कर रहे हैं इसलिए यूट्यूब का नहीं है
यूट्यूब का नहीं है सर ये तो दिन का राहुल पुराना किताब
यूट्यूब है ना
हाँ यूट्यूब का
गुड मॉर्निंग गुड मॉर्निंग
हेलो
नहीं बोला है स्क्रीन को करना स्क्रीन को करना ये हो गया मीटिंग कर रहे हैं
Tem participante. Sempre do time, não sei, não é isso. Tá tudo correto. Esse o político,
फ्लोटिंग कहाँ चलती
ये सी प्रॉब्लम आ जाएगी ये सब देखा जाए अच्छा तो डिस्प्ले सेट उसको करेगा साथ में हाँ
नहीं मेरा नहीं हो रहा था ये वाला मेरा नहीं होगा ये वाला नहीं होगा इसमें गलत करना है सेटिंग्स इसमें गलत करना
Namaskar, good morning to all. I request our director to bring the dignitaries onto the dais. Namaskar, good morning and Suswagatam. Dignitaries on the dais, Professor Umesh Vakmani, President UGC-DAE Bangalore, Honorable Professor Rakesh Singhai, Kulguru, Devi Vishwavidyalaya Indore, Professor Kaustubh Priolkar, Director UGC-DAE CSR, dignitaries of the dais, professors and friends from Devi University, scientists from RRCAT and IIT, faculty, technical staff, students and friends. I welcome to you all in this event celebrating 36th Foundation Day function. So 36 is a good number, which shows that age-wise we are still young and working at its full capacity. They gives us an opportunity to celebrate our achievements as well as take stock of things for improvement. Generally, we say for persons also that as we age, we become more wiser. And so hope we that in the similar way, the institute should be able to more capable in its targeted goal. How successful we are will be reflected in the annual report to be presented by our director. This institute is founded by visionary Professor V.G. and we are celebrating his birth centenary this year. He founded this institute on a theme best described by Rija in Rigveda, Ano Bhadra Ratvo Yantu Vishwata, that is, Sabvarse Uttam Vichara Nidhu. Let the good ideas and thoughts come from all directions. He envisioned consortium to be an open platform where researchers from universities can interact with researchers from premier institutes of India as well as DAE scientists. The facilities of DAE are made open to university researchers through this platform, providing equal opportunities for university researchers from less affluent universities and colleges. In this endeavor, the task of consortium is to seek help from both DAE establishments and universities to fulfill its mandate. As universities are major beneficiary of this institute, the consortium has been thought to be located in the university campus. I thank all the DAE institutions for their excellent support to our institute over the years, and the faith and cooperation has been growing every year. In Indore, we have been getting admirable support from RRCAT Indore, and we have been operating the synchrotron-based research program very successfully. On this occasion, I would like to place on record the help and support received from DAE institutions. Further, we have also got exemplary support from Devi University, Vishwavidyalaya, and our mutual cooperation and help is commendable. Every Vice Chancellor and Head of the Department of the Physics has wholeheartedly supported the effort of consortium, and we are thankful to them. We are in university campus with name belonging to a very pious and visionary lady with Praja Hit Sarvopari mantra. We at consortium also mandated to put forward the interest of universities as Sarvopari. And here we seek help from current Kulguru. I take this opportunity to plead you against a visionary and supporter of Abhyuday Bharat movement, and he has initiated many new developments and initiatives for the growth of university, which is commendable, and we appreciate that. The growth of consortium rests on your support, and we are starving for good laboratory space and request you to help us in this regard for capacity expansion. So I will humbly once again look forward to your guidance and address this issue, and I welcome you, sir, on your first visit to consortium wholeheartedly. The institute has been fortunate that many very high-level academicians and science leaders of the country has visited this institute on the occasion of annual function. Professor Raja Ramanna,
Recording in progress.
Dr. Abhilka Kodkar, Professor Ajay Sood are few names known to everybody. Today, we welcome another stalwart of science in the country, Professor Umesh Wagmare. We welcome you, sir, and look forward to your lecture. I once again welcome you all on behalf of consortium. Those who have joined online, I welcome you all. Namaskar. And now I request our director for a floral welcome of the guest. I request our director for his annual report. Yeah.
गुड मॉर्निंग, नमस्कार एंड आप सभी को इस 36th एनुअल डे की बहुत बहुत शुभकामनाएं। प्रोफेसर उमेश वाघमारे, प्रेसिडेंट ऑफ JNKSR, प्रोफेसर राकेश सिंघई, वाइस चांसलर ऑफ DAVD, distinguished guests, my colleagues and dear students. This UGC-DAE consortium was set up with an objective to help university researchers carry out research in frontline areas by providing them access to the DAE major facilities. And over the last 36 years, this institute has stood up to its potential, stood up to its mission. And this can be seen from basically 4 counts. The trust of Department of Atomic Energy in this institution that has allowed us to grow, increase our number of centers and nodes across all over India, increase our facilities at synchrotrons or neutron sources or cyclotrons, participation in their programs. Secondly, the trust that UGC has in us, wherein they have supported us through fundings and supported all our endeavors and expansion plans over the years. The third and most important one is the trust that the users have in us, and they have always come back to us. We have continued users, we have generations of users who are coming and again to these centers for carrying out their research. And the fourth and perhaps the most important one is the trust that DAVD has in us, in that sense that they have hosted us for last 36 years, they have cooperated with us, and I hope that this cooperation and this trust that the university has in us will continue in over times to come. Today we are 4 centers strong. The biggest one and the main center is at here Indore, which is basically to take care of the synchrotrons, Indus synchrotron utilization by university researchers. And this center there operates 3 beamlines. In addition, we have state-of-the-art in-house facilities, mainly focusing on low temperature and high magnetic field characterization of samples. Other centers are in Kolkata, where we take care of cyclotron utilization, which is available from the Variable Energy Cyclotron Center there. And here the major thrust is on the INGA project, where the center has contributed significantly. We also have facilities for radiation biology and chemistry research, and we are going to install a gamma ray chamber very soon. This center also looks after the newly established Bhubaneswar node, which is at the Institute of Physics in Bhubaneswar. The third center is in Mumbai, which of course takes care of the utilization of neutron spectrometers by university scientists, and we also have our own neutron spectrometer there. In addition, we have some unique facilities like spark plasma sintering and ESR spectrometers, and of course, we also provide access to other BRC facilities which the DAE has opened up for the university researchers. The youngest center is the Kalpakam Center, which is very different from other 3 centers in the sense that the facilities are funded there by the DAE, and along with the 200 kV ion accelerator. And here the characterization facilities span across physical, chemical, and engineering sciences. Now, let me focus on to the Indore Center. The facilities here span over almost 6 or 7 areas of research: thin film deposition, scattering, transport, and thermal and magnetic measurements, spectroscopic techniques, microscopy, crystal growth, and of course also a small theory group. But the unique facilities amongst these are the diffractometer, which operates not only at temperature dependent but also in the high magnetic field of 8 Tesla, the transport and thermal magnetic measurements, which can go down to millikelvin range, and also in fields up to 16 Tesla. Most board spectroscopy, which is another unique facility which comes from, which operates within presence of magnetic field. the UHV STM that was developed here at the center, and of course the three beamlines that we operate at the Indus Synchrotrons. Two of them which we have developed ourselves. The third one, which is the BL13 at Indus 2, which was handed over to us very recently, and our scientists have made sure that it can be used by the university researchers. The backbone of all these is the cryogenic facility that we have, and we generate both liquid nitrogen and liquid helium, which is for our research, as well as we support some nearby institutions in terms of liquid nitrogen. The impressive number that are to be looked at is almost 100,000 liters of cryogenic liquids that we produce every year. And of course, the automatic helium gas recovery system, which has almost 95, and we recover almost 95% of our helium gas. The capacity and the expertise that has been built in this center, cryogenic center, is acknowledged not only by our peers, but also by the manufacturers of the helium plants. And I think that is something that we have to be very proud of. Coming to our beamlines, this is the oldest beamline that we have at Indus 1, which is the angle integrated photo emission beamline. It operates in the energy range of about 10 eV to 200 eV, basically focusing on the valence band and resonant photo emission spectroscopy there. And one of the examples that is shown here is the valence band studies that were performed on these BIFE-03 films, which were targeted for solar energy research. And the other beamline is the soft X-ray absorption spectroscopy beamline, which we can do record ages right from carbon to all the transition elements. So that goes from about 100 to 1200 electron volts. And of course, you can also do XMCT, and some of these examples are shown here. And this has also been heavily used, resulting in almost more than 200 publications over the years, and including researchers from institutions like IITs and JNCSR. The recent beamline that we have got is the BL13, which was an assigned beamline that was handed over to us for operation very recently. And now we can say that this beamline is all ready for doing experiments like high resolution single crystal and multi-layer diffraction, reciprocal space mapping, X-ray reflectivity, diffuse scattering, grazing incidence, both in plane and out of plane, and also high throughput, high quality powder X-ray. And these are some of the capabilities that you can see here in terms of reflectivity, fringes, or the reciprocal space map that tells you about the strain distribution in multi-layers, or the epitaxial growth of thin films that you can do using a 5-scan. Also, you can do the high resolution, high throughput, so quote unquote in operando kind of diffraction patterns you can record, because the measurement time is only just few minutes. And you can also see one example that has recently been accepted here, where you can see that by shining light, you could also track down the changes in the domain structures or domain rotations in this ferroelectric thin film. Coming to our Kolkata center, as I said before, the major highlight of this center is the participation in the INGA campaign, and where the center has contributed immensely in developing this digital data acquisition system, which has been almost like the major or the heart of this INGA use of INGA equipment, which has resulted in almost 30 plus publications in very prestigious journals like PRL, and more than 10 PhDs have come out, and few more are in the pipeline. Of course, there are other research that is also going on in terms of medical radioisotopes here, and doing the understanding the fission process. In the biology side and chemistry side, we have a motorized inverted fluorescence microscope using which very good studies on understanding targeted drug delivery in terms of cancer cells have been done. And one example is shown here, wherein the uptake of morine and gadolinium dopamine are shown here. Also, this is the new gamma irradiation chamber that is being installed presently in our new building of the Kolkata Center, and we hope that within a month or so, this facility will also be operational for the users to use it. There is of course a small group which is also doing some condensed matter research, and one of the examples on this half-Whistler alloy is shown here. Now about Mumbai Center, where this focuses on neutron beam research at Dhruva. And apart from using the wide variety of neutron spectrometers that are available from the solid state physics division of BRC, we also have our high resolution neutron powder diffractometer, which has a capability of working in presence of magnetic fields up to 7 Tesla and temperatures from 2 Kelvin to 300 Kelvin. And very soon we will be extending this temperature range to almost about 800 Kelvin, which is, you can see the resolution here, and I will also show you examples that prove what I am saying. But other than that, you also have some other BRC facilities which include the pelletron at TIFR and the neutron activation facilities and other material science, spectroscopic and microscopic facilities that BRC has and has opened up for the users. The capability of our neutron diffractometer can be seen from these two examples, wherein we have been able to solve magnetic structures of highly incommensurate magnetic structures. First one is in holmium-free cobalt, where there is a transition below its near temperature, and the magnetic propagation vector really changes with temperature, and that can be seen here from the diffraction pattern. And also this sample of lutetium ferrate or LeFeO3, you can very clearly see that we could in fact see the small magnetic peaks which could very clearly, by which we could solve the magnetic structure of hexagonal phase. At Quantum Center, we have the 200 kV accelerator, and although this center is small, it caters to a large number of users. Almost 100 users have used these facilities in these 11 months that we have of this year, and quite a good research was also carried out both in-house as well as from the user side. One example I have shown here, wherein you can see the Rashba spin orbit coupling and very curvature driven asymmetric MR as well as anomalous Hall effect measurements. And also this is coming from a CRS project wherein they have tried to modulate the thermal conductivity of an half-Whistler alloy and given the reason for how that's happening. We also have some computational facilities there, and that allows them to do some density functional calculations on compounds of their mutual interest. Of course, all this is for the users, and we have about 1,500 users visiting our all 4 centers and using the facilities every year. And you can see from the map that our users are actually distributed all over the country from across the length and breadth, whether you take from east to west or north to south. And this is possible because of the user program or the user portal that we have, wherein any university or institute person can use our facilities in modes. One is of course the long-term project mode, wherein we give some financial support in terms of either a student or some contingency grants. And these projects are about for 3-year projects. And this and there is a call for this project, and there's an evaluation also, and through which you can come to our centers and use these facilities. And at present, there are about 374 projects that are operational, and we spend about 5 crores of rupees from our budget to every year to fund these projects. The other way that you can use these facilities is a one-time use, wherein you just have to put in a proposal for use of a specific technique or a specific instrument, and then you are given a beam time or you are given an instrument time, and you can come and use it. So in this mode, there is no, we only see the feasibility of experiment and we only see the quality of samples. Not much of scientific rigor is given here. It is basically open to use, and also we don't expect that that the publications or the results that come out of this, our scientists or faculty are authors in. We generally say that just acknowledge the facility. And over the years, the training that this institute has provided to the university users has resulted in a sort of an inversion, which you can see here, that the blue bar, which tells you about the acknowledgements that have come, it has the publication that have only acknowledgement from our institute the number has increased more than the publications that have we as authors, right? So that it is something that tells us that this institute is now really functioning as a user facility. Okay, we have our in-house research, we have our collaborative research, but we also cater to a wide variety of users as a user facility, which is something that we have to be very proud of. The quality of research that is done is no less, both in-house research, as you can see from some of the publications that I'm highlighting here. This is just a snapshot, nothing to say that we have publications, regular publications in journals like Physical Review B and Advanced Functional Materials, and chemistry journals like JPC and others. But this is coming from our in-house research from different centers, but it also comes from the users. And you can see that equally good publications are coming from users in very high impact journals in different areas of condensed matter and physics and chemistry. We also have outreach programs, and specifically at Indore and Kolkata, because Mumbai and Kalpakkam are within the DAE establishments, and therefore security constraints are there. At Indore, we welcome groups of students to come and see our facilities, and almost they spend a day or so at the institute. At Kolkata, we have training programs in collaboration with the State Department of Biotechnology or State Departments of Science and Technology for college students and university students. And we are very soon planning to extend it to even areas of Northeast. We also hold large number of conferences, seminars, and workshops. The highlight being the IUMRS ICA, which was held in last December. Other thing that we have is these awareness meetings for university teachers and prospective users. Every year we have 4 such meetings, online meetings, wherein about almost 800 participants participate, and wherein the capabilities and the know-how about our facilities are given to them, and based on that, these university researchers propose for use of our facilities. We also have thematic workshops. One of the most successful series that we are continuing with is the neutrons as probes for condensed matter. This year was the 21st such workshop, but there have been other workshops on neutron analysis or neutron data acquisition, which are not counted in this series. But this is the most continuing series of this, and we plan to also extend this to other areas now. We also have discussion meetings, and this year onwards, being the birth centenary of our founding director, we have started a VG Memorial Lecture Series, and the first lecture in this series was recently given by Professor D.D. Sharma. Of course, these are some glimpses of other units, other events that are celebrated at this institute. So I'm not going to spend much time on that. And another thing that we are very proud of, and I will always say so, is the sports activities. If you visit any labs, apart from the wide gamut of instruments and the very impressive instruments that you see, you will also see very glittering trophies, right? And so that is something that we are proud of, and we should be proud of, I think, because that's what the students and faculty members participate, and it's a highly competitive event that happens every year. These are some of the awards and honors that our faculty members and students have won. And this year, we are extremely proud that two of our scientists, Dr. Sandeep Bugre and Dr. Reddy, have been elected as fellows of the National Academy of Sciences of India. And let us congratulate both of them. There have been also other honors that have our scientists have won, and also our students have regularly won these Best Poster Awards and Young Scientist Awards, and I hope they continue to do so in years to come also. This year we have awarded 18 PhDs, to 18 students have graduated in this year, and although 8 from CRS projects, but I'm sure this number will be much larger than that, because this is the number that we have information of, right? So it will be, if not more than this, it will be almost equal to this number of 18. Apart from that, we also welcome undergraduate and postgraduate students, especially from the AVD, to do their projects, and many of them come here. Then this is the number of students that have done projects this year, and we hope that we'll continue to do this. So at the end, I would like to focus on some of the new initiatives that we plan to undertake in the coming year. Talks are in place with the BRC for a electron microscopy lab at the Mumbai Center. The funding of this will come from BRC, but the management and operations of this electron microscope, which includes a 300 kV very high resolution electron microscope, an FIB ACM, and an atom probe microscope, which are being planned to set up at the Mumbai Center, the new campus of Mumbai Center. In addition, superconducting cyclotron of VECC is operational, and now we are trying to extend these facilities to university users, and very soon we will have an awareness workshop so that this facility can be extended. VECC very recently also developed a medical cyclotron, a prototype medical cyclotron, which would be then commercialized and given to different hospitals. We are trying to get this prototype model installed at our center or say facility where we can make it available for university researchers. RRCAT has given us a probe station or a beamline, whatever you call it, at their free electron laser facility, and a new pump probe spectrometer or facility is being established there, and that will be operational in the coming year. We are looking for land to hold up our expansion plans, or to go ahead with our expansion plans, and I would request the Vice Chancellor to help us in this matter. Another thing that we are planning is the laboratory with the novel physics experiments that Professor R. Srinivasan developed after leaving this institute, while at RRCAT and then later from his house. We want to establish that lab here at R. Srinivasan lab, which will be useful playground for our new students. It will be part of their training, but not only for students, but we also would like to open it up to teachers from Madhya Pradesh and other states, so that they can come and use this, learn from these experiments, and go back and install that in their own base. And I think some of these experiments are highly needed, because they are very good experiments, and in the light of new education policy, it will be a very good facility to have at our center. As I said, the neutron thematic workshops have been continuing over the years. We plan to start this series with, in collaboration with RRCAT on synchrotron and in collaboration with VCC on cyclotron or radiation-based research. And two such workshops, both on synchrotron related and cyclotron related, will be held in the coming months or the early months of the 2026. And the new lecture series that we have already started, I have talked about. So, thank you very much, and once again, wish you all a very good annual day.
I thank the director for his annual report, and now I request Professor Rakesh Singh, Honorable Vice Chancellor or Kulguru of the Vela Vishwavidyalaya, for his address and comments. So,
Respected Professor Umesh Maharji, the Director of the UGC-DAE Consortium, Professor Kaustubji, Professor Basant Sathe, the distinguished scientists, learned faculty members, dedicated administrative staff, and most importantly, the brilliant research scholars and students present here today. Namaskar and very good morning. It is a distinct honor and a profound privilege for me to stand before you today, not just as Vice Chancellor of DAVV, but as a proud partner in this incredible journey of scientific excellence. To be invited as a guest of honor for the 36th annual function of this prestigious center is a moment I cherish deeply. Celebrating the milestone, the 36 years is a significant milestone in the life of an institution. In human terms, 36 is an age of maturity, stability, and peak performance. Similarly, looking at the trajectory of this center, I see an institution that has moved beyond its foundational years and is now a powerhouse of sophisticated research. You have spent over 3 decades bridging the gap between the university system and the high-end research facilities of the Department of Atomic Energy. You have democratized access to world-class science, making sure that a researcher from a remote university has the same access to the synchrotrons or low-temperature facilities as a scientist from a premier national institute. This center stands as a testament to the idea that science has no boundaries and resources must be shared for the greater good of the nation. The DAVV and UGC-DAE bond as the Vice Chancellor of DAVV, I view the UGC-DAE CSR not merely as a neighbor on our campus, but as our intellectual heartbeat. The relationship between DAVV and this consortium is symbolic. We provide the academic ecosystem, the fresh flow of young minds, and the structural support. You provide the cutting-edge exposure, the rigor of national level laboratories, and the vision of the Department of Atomic Energy. Together, we have created a unique hub in Indore that puts our city firmly on the global map of material science and physics. To the students and research scholars present here, you are the soul of this celebration. We live in an era where the lines between disciplines are blurring. Physics is talking to biology, chemistry is merging with engineering. This center is the perfect playground for such interdisciplinary magic. My advice to you is very simple: to embrace the failure, to collaborate, and think for the nation. As we celebrate the 36th year, Let us also look forward. I assure you that DAVV will continue to extend its unwavering support to the consortium. Let us aim to increase our joint publications, foster more patents, and perhaps create an incubation ecosystem where the fundamental science done here translates into technology for the masses. I congratulate the director and the entire team of UGC-DAE CSR for maintaining such high standards of integrity and scientific inquiry over 3.5 decades. May this 36th annual function be a celebration of curiosity, a festival of logic, and a renewal of our vow to serve the nation through science. Thank you very much, and Jai Bharat.
Thank you for your Ashirvachan, sir. Thank you very much for your guidance. Now I request our Center Director, Kolkata Center, Dr. Sandeep Kupre, to introduce the chief guest to the audience.
Namaskar to all the dignitaries present and all my colleagues present in the physical mode as well as the online mode. In the morning, as my colleague Dr. Sake has reminded us that it is the 36th year, and I take the permission to say a few lines in Marathi. की श्रीकडे हीच प्रार्थना आहे की कोणाशी 36चा आकडा नसावा. And I'm sure the meaning my colleague Sake will explain to you. When I was given this task to introduce Professor Wagmare, I again go back to my mother tongue Marathi, where I am reminded of a line by the legendary poet Gati Mandurkar, that this attempt best would be summarized by a line which is said, कि ज्योति ने तेजाची आरती. So if there are any mistakes from my side, I owe an apology to the august speaker. And whenever we talking about the introduction to a speaker, most of the information is readily available in the public domain. But what is not available in the public domain are folklores which really reflect the human being behind a charismatic academic leader and a mentor. So I'll just take a minute to describe an incident we had. We had developed as a part of an ME course a novel nuclear instrumentation thing, and all my colleagues said at that time we should publish in NIM, which is considered to be a prestigious journal in nuclear instrumentation. But some of us felt that since it was of use to the senior, to most of the nuclear physics laboratories in the country, we should publish it in Pramana. We sent off the publication in October. Diwali chali gayi, hum log annual day ho gaya. We had in January we had our GB, FC, everything. February passed, year-ending came. We did not hear back from the journal. So all my colleagues were beating down my neck that why did you delay this publication? So we wrote to the editor-in-chief that, sir, we are having this agonizing wait for 4 months. Can you please look into it? And to our surprise, on a return email, I got the message, I will look into it today. And there are no marks for this August audience to guess who the editor was. And he's our esteemed speaker. And by the end of the day, we got an update and soon the paper published. So that, I'm sure many of my colleagues who have published in Brahma will have a similar experience which brings out the man behind the charismatic leader. As I said, these are the things which become a part of folklore, which are never reflected in the CV or the information that are available in the public domain. But we as academic people are truly blessed to have editors, the former Professor Wagmare, who goes beyond his academic duty to help us out in publication. Let me now complete my formal duty of trying to introduce to this August audience. I'm sure it's blasphemous on my part to introduce him to this audience, but well, let me just complete it. There were a few glimpses of his academic endeavors, which are, as we in our generation knew, was an advertisement from the Onita TV owner's envy. And his CV is truly a personification of that advertisement. Professor Wagmare, following his BTech degree in engineering physics, went on to get his doctoral degree from Yale and had a postdoc staying at Harvard University. And then he joined as a faculty of the NSCR, Bangalore in the year 2000. Currently, as I said, I was in Diadema, I should mention him as a professor of physics, first at the institute or the president, I think. So as we all are familiar with the dual nature of affiliation, he wears several hats with equal competence and equal mentorship. Professor Wagmare is the recipient of several prestigious national and international awards, including but not limited to the prestigious Kishore Bhatnagar Prize, B.M. Birla Science Prize, Infosys Prize, and of course, J.C. Bose National Fellowship. He is also the recipient of MRSI Medal, CNRO Prize Lecture, and Distinguished Material Research Scientist of the Year. He is also a recipient of the Distinguished Leadership Award of the Material Research Society, USA. He is a fellow of all the three prestigious academies of India and also has served as the president of Indian Academy of Science, Bangalore, from the year 2022 to 2024. Professor Wagmare is an internationally renowned researcher for his contributions in the field of condensed matter theory and material physics by employing first principles of modeling to understand and predict microscopic mechanisms that govern a wide range of material properties like ferroelectricity, topology, and energy conversion. So, without much ado, I would really request Professor Wagmare.
Thank you. Good morning. It's a pleasure to be with you on this very special occasion of the 26th Foundation Day of the UGC-DAE CSR. My greatest appreciation for the Institute for a variety of things. Before I start my technical talk, I wish to make a few remarks which I think will also appeal to those who are not from physics background. This institution is contributing in a very significant way to the nation. One is it builds its own instrumentation to a great extent, which is very rare trait in India today, and that has to be appreciated. And these are instruments which are fairly cutting-edge type of equipment. Secondly, they share these facilities with everybody in the country, free, specifically universities, which is again very commendable. This is the need of the nation. The universities have been ignored in the last several decades, and that gap is being filled in and supported by this center. So, that's second point. Third, it is in the premises of this great university, the India Vishwavidyalaya, and they maintain such a beautiful relationship, and it's very heartening to see that this symbiotic relationship is going to only help both institutions to grow in the future. So my compliments of that to both of you. There are a few other remarks I wish to make. You refer to me as an editor of Kamara. I'm no longer an editor, but if you look at the publications in Kamara, they are mostly from theory, theoretical physics, nonlinear dynamics. And this is to highlight that experimental physics in India, particularly, is in need of organic. It's very easy to do theory. In fact, you will see my technical talk is on theory. It's a lot easier than experimental work. And that sort of almost, I mean, if you see phenomena, you will feel, is experimental physics going to extinction or not? And there your institution is supporting the nation. So that's fourth point on which I wish to compliment all of you. Wish you really great success in continuing your activities in the domains that you have taken up in these four sub-sectors of UGC-DAE CSR. So with that, I will start my technical talk, and there are two sort of warnings I wish to give. For those who are experts, this may be a little elementary, but I have prepared it for the students in the audience, and they are the future of our nation, so I hope this will be a good introduction to the students. And also, for those who are not from physics, this may be a bit distant topic, but I'll make an effort to at least give you a flavor of what we do and how we think about some of the modern ideas in physics, particularly quantum physics. Let me get started. So, all of you know that theory has been very powerful in physics, and particularly condensed matter physics, which is a strong focus of this center. And theory has been used to understand materials. Theory has been used along with computation. When I say theory, it's a combination of theory and simulations. It has been used in prediction of new materials. It has been used in prediction of new phenomena. And in this talk, I will show that you can use theory to predict a new set of experimental techniques, which I feel is very rare. And I'll give you one example. Maybe 100 years ago, Raman spectroscopy was, of course, tried with scientific work from India, and it was predicted by the theorists like Dirac and Heisenberg in 1921. And it took 5 years to develop this technique for Raman, and at that time it was absolutely a great feat of accomplishment. It was an overnight experiment in the Association of Graduation of Science to verify those ideas and establish that it can be done in the first place. So this talk will be sort of the first part of that type of work. Theory is predicting something new, which we have some partial experimental verification. Okay? So the work, and I also wish to share the idea of what I will tell you, came from the student, R. Bhuvaneshwari, who's just completing a PhD now. And experimental work has been taken up by Mandar Deshmukh in TIFR Bombay, and with some partial success in verifying the ideas that I tell. So what I'm going to tell you is a new type of spectroscopes, which are based on the concept of quantum geometry of electrons in crystals. And the work is supported by my UGC Ghosh National Fellowship and also the Department of Science and Technology, which supports my institute, Jawaharlal Nehru Center for Advanced Scientific Research, as an AA institute. So this is a proposal based on first principles theory. Why? What do we mean by first principles? For those who may not know, we don't use any experimental information to do our analysis at all. It starts from fundamental principles in physics, like quantum mechanics, Planck's constant. There are no parameters which we use to fit experiments, and that's why they are called first principles, or some people call it ab initio theory. We start from scratch in developing this theory. And we predict a new class of spectroscopies which are based on quantum geometry and demonstrate it within vibrational spectroscopy into the materials. And it's also in celebration of 100 years of first observation of Raman effect. Raman spectroscopy, by the way, is also a vibrational spectroscopy. So we were very delighted that we are coming up with something new to do what Raman did 100 years ago, but with a fundamentally different physical regime in this case. This picture, I'm sure many of you have seen in popular science magazines, where light coming from a distant object in the universe, when it passes near a very heavy gravitational object, It bends its trajectory to meet her, which otherwise in a straight line we would not have expected. And this effect is called gravitational lensing. And this effect arises not because light photon is attracted by this heavy mass due to gravitational force, but it happens, as you will see, because the space-time through which light traverses is curved. Okay? So the curved space-time is what causes it. And this curvature is basically defining the fact that the space-time is not flat. It's a geometry of the space-time. So can we see this from electrons? Is the question we pose. And the answer is yes, and that's where the concept of quantum geometry comes in. So I'm going to start with a fairly longish introduction to quantum geometry and not sort of give too much time to the actual theory work, which may become a bit technical for some. So let me tell you what is quantum geometry, and at least if you learn about it, I think that's the take-home message from my talk. And these are ideas which are becoming very popular. So if you know electron, you have to think of it as a wave, a dual particle wave picture. And in a classical sense, it has a momentum which is given by mass times velocity. And if you think of it as a wave, momentum gives you the wavelength, so the de Broglie relationship, and h bar k is the wave vector, pi by lambda. Okay? So this is a quantum picture. In quantum picture, there is a wave function which represents this electron as a wave, and that is given by e raised to ikx. It's called plane wave, which is using Euler's relationship as a simple form. The thing to remember is the momentum quantum vector is the quantum number k. K is the quantum number, which is a continuous quantum number. It's not an integer quantum. And energy of the electron, it's a free electron, meaning it doesn't feel any force due to external objects. Is basically d squared by k. In classical physics and in quantum physics, it's k squared by k. H bar is the Planck's constant, which defines the quantum form of picture. Okay? So k is the wave vector, which is a continuous quantum number, like hydrogen atom wave functions are NLN quantum number. This is the quantum number for electron, which is free. When you place this electron in a crystal, it feels periodic potential which comes from the atoms which are arranged on it. And this potential naturally affects the wave function of electron as it traverses to here. So first thing you will say is when electron has a wave function which is center on each atom on this lattice, this is the wave function, and each atom has its own electron function. That's a wave function. But once the atoms are closer together and electron wave functions overlap with each other, they modify these wave functions to minimize the energy. And to do that, what happens is basically you get a wave function which has this component, which is called self-periodic part of the wave function. And the second one, the dashed line, is a plane wave with a periodicity which is longer than the periodic lattice constant. Okay? So this is called Bloch's theorem. In for electrons in crystal, E is psi in k is U periodic times the non-periodic part, the envelope part of the wave function. And again, to remember, k is the quantum number, just like a free electron. So nothing changed much. K is still a continuous quantum number, but now it is restricted to a single unit cell of the reciprocal space lattice. That's the change. And that's because of the periodicity. Reciprocal space lattice gets defined because you have a lattice in period space. Okay. So h bar k now is called distant momentum rather than momentum of a free electron. Wonderful. The energy of a nearly free electron gas was a parabolic form like k squared by 2l. Now, once you have a crystal potential, these energies get modified, and you will see that there is a gap opening up at basically some special point, and these points are called as zone boundary points. Boundaries of the Brillouin zone, which defines a periodic unit in the reciprocal space. Yeah? So this type of gaps open up, but elsewhere you will see the wave energies are more or less very similar to the picture. Okay? So gap opens up at the special points in this region in which you can study the electronic structure. This is called electronic structure of this electron in the crystal. You just have to focus on wave vector which belongs to this structure, and that's the Brillouin zone. Okay? I hope all these are clear, and students, you are welcome to stop me at any stage during my talk. Wonderful. So this is what we mean by electronic structure in general solid state physics. Wonderful, and this is an example of phosphorine. If you make a lattice of phosphorus atoms, it is very similar to graphene, but it likes to distort because phosphorus has 5 electrons, unlike graphene. And this is the electronic structure you get. This is energy of an electron wave. And on the x-axis is basically the wave vector, which belongs to the Brillouin zone I explained. Brillouin zone of phosphorine here and shaded region. And you see these special wave vectors are the labels are different points in the Brillouin zone. So when you want to examine electronic structure of electrons in a crystal, you usually look at sort of band. This is called band structure along this high symmetry lines and points in the Brillouin zone. And that gives you a very clear picture. Here you can see that the unoccupied space, which are reduction pattern, occupied space, which are valence bands, are separated by a gap, and that's why it's a semiconductor. If you place another atomic layer of phosphorus of each other, it becomes metallic. You see now there is no gap separating occupied states from unoccupied states, and that's metallic. And that's the beauty of this Feynman's matter physics. By changing size, by changing chemistry, by changing structure, you can tune the properties of the system, and you can use them in different types of it. When this is have balance and conduction band overlap, and that's why it's a mechanism. So electronic structure has no information about quantum geometry. This is the point. At the moment, all of this you must have seen in solid state physics textbooks, and this is something you're familiar with, but this is to set the stage. And also to highlight that by looking at this type of picture, you can't really tell the geometry. What I mean is the quantum geometry. Okay, so to tell you first, there's another feature of this electronic structure which you may not have realized in textbooks is this electronic structure is periodic in reciprocal space also. When you think of distance, of course you think of periodicity in real space in terms of the atomic structure. And of course, X-ray diffraction gives you reciprocal space description of the crystal lattice, and it already tells you that there is some very fundamental link between the elements. Spaces, but energies are also periodic in reciprocal space. For example, energy of this state is same as energy of this state, same as this. So this is k-axis in the reciprocal space. The same is true for the occupied band. Yeah? So there is periodicity in energy, which is well known to you. It's called extended versus periodic zone scheme. But there is also a wave function which is periodic. Means wave function of this state is identical to wave function of this state. Okay? So this is important to realize because we will build on this now. So you have periodicity of wave functions. And the periodicity is given by below. Okay, so if that's the case, this is the Brillouin zone, the unique cell in the reciprocal space, and if electron can move along this dash, you will find all the dash blue line along y direction, but when it closes, electron moves from this end to this end, it comes back to itself, its original position. And what it means is this Brillouin zone you have to fold it. So if you have a paper, you will fold to make a cylinder, and then the cylinder will be folded to make a torus because of this periodicity. So electrons in a 2D-dimensional lattice already are having quantum numbers which form a torus. And that's where you can see geometric features are moving in the quantum mechanical sense. Yeah, so, for example, the lines I'm showing you here, the red line may go around the perimeter of this torus, the red line, so black one will go along the circle which is cutting this torus. Yeah? So these are the ideas. But the key point is electron moving around across the Brillouin zone from here to here actually forms a closed path. Yeah? And that's where geometry comes. Now I'm going to give you a demonstration. All of you can see this pointer in my hand. I'm going to hold this pointer orthogonal or perpendicular to my arm. Okay? And it's a vector in 3D space. You can think of it as an electron field. Yeah, and my arm is the k vector in the Brillouin zone direction. That's my arm. And now if I move my arm by maintaining the angle between the vector and the arm, bring it to the vector by low propagation, and bring it back. You see, what has happened is it is rotated by 90 degrees. And this rotation is like a phase factor which the electronic wave function picks up, depends only on the solid angle that might close tangent. And that's what is called geometry phase. The phase factor which is picked up is called geometry. And probably the concept of geometric phase was first thought by Hunter in Bangalore. He was in Bangalore University. Right? But what in quantum physics, he thought about this idea in optics. In optics also, this like this vector, you have polarization of electromagnetic field and same ideas are that. So Hunter thought in 50s of these concepts. In 80s, Michael Bailey in UK thought of the same thing, quantum. And that's why they are called Bailey physics. These geometric phases in quantum physics are known as Bailey. And this was one of the most important developments in quantum physics. As you know, quantum physics was developed in 1920s, 100 years ago. We celebrated 100 years of this. But the idea of this geometric structure in quantum physics was not realized until 1984. 60 years. So this is a modern idea, relatively, still 40 years old. But it was thought of years. And that's where the geometry in quantum structure comes. Okay? Wonderful. So I hope I'm going slow enough and things are clear. Yeah? Wonderful. So you now know what is geometric phase and what is other beautiful thing research that I wish to share with you is the geometric phase of the quantum wave function. I already defined this is the lock wave function and K is the quantum number, continuous quantum number, which belongs to the Lorentz. So, to calculate this geometric phase of a lock function, you use this formula. This is called Bailey connection, and you will see it tells you how the wave function at A changes with respect to K and goes to the next. And that's called Bailey connection. How wave function at this point is related to wave function at this point. That connection is Bailey connection. And if you integrate it along the closed loop, this is closed loop because this is across the platform, you become a Bailey phase gamma. But then here is a new result for you. Oh, the average position of an electron in a crystal is given by this Bailey phase. No, that's not so obvious. In fact, there is a big surprise here. All of you work with crystals, all of you know electrons are with the crystal, but you know, and if you want to calculate dipole moment of the crystal, it's a very interesting problem. You cannot calculate dipole moment of the crystal by just knowing the electron density. For a molecule, you will say, of course, we have density, we calculate dipole moment as the source moment in real space, but you can't do it for solid because density is an infinitely distributed extended function, and position is it's minus infinity to plus infinity. You can't do it. That was an open problem. It was solved by these methods by W and showed that this actually relates to variable. So let me tell you that it's a trick. I mean, that's when we appreciate why the geometric factor is very important. So what things is there is, although you cannot calculate dipole moment of a crystal, you can calculate changes in the dipole moment. As you change, say, if you apply electric field, as you know, dielectric of course generates polarization. And change in polarization is a measurable quantity. And that's what you can calculate, and then they show that it can be related to this. And change in polarization, as you see, it's also ideal change in persistence. So that's where this sort of ideas are. Okay? So remember, geometric phase of an electron with a crystal tells you the average real space position. Yeah? Within two pi means within the line space. Okay. So if you have an electron in 2 dimensions, this is the this is kx direction, this is ky direction. Electron can move along x direction along this blue line, or it can move also along y direction along the d line. And if Bailey phase along x direction gives you the average position along x direction, gamma x. The Bailey phase along y direction gives you average position along y, average y coordinate. Okay? And then since it's a 2D system, you can have a Bailey potential, which is a vector vector potential, and very phase is given by two figures, and very curvature is curved in basic open space of this connection, and we will see what it means in a minute, and gamma alpha gives you equation. Now what you will see is, if omega is non-zero, what happens? Omega is the very curvature. Now remind you, I introduced you space-time being curved. Now we are thinking of electrons. So omega is non-zero, very curvature is non-zero. The quantum phase space time of electron is curved. That's the result. And I'll convince you of that. Using the ideas that we learned today. Okay. If you apply electric field along this direction, electronic position goes from here to the next position. See, this to this. But if the wave phase along y direction changes with this change, you will see the average y position is changing too. So as electron moves along x direction, due to this very curvature, its average y position also changes. What it means is, applied electric field causes a velocity along transverse direction. And that's very not easy to understand, right? Because usually you expect that if an electron is moving in a magnetic field, it will feel a transverse field. Sure. But here there is no magnetic field applied. But simply because of the curvature, electron shifts along y direction in the very curvature. Zero, and that's why we show here as a function of kx in the x direction, actually the y position changes, and that gives rise to shift current, or what's known as Hall effect. But this Hall effect is, all of you know Hall effect, but this is in the presence of no magnetic field, and that's why it's called anomalous Hall effect. Okay, so the first measurable effect that you will see experimentally as a consequence of non-trivial quantum geometry is the Hall effect. Anomalous Hall in particle theory. So if you have a metal in two dimensions, this is the Riemann zone, and suppose this is the Fermi surface, meaning these states are occupied and other states are unoccupied. That's the definition of a metal in 2D. If you connect the wave phase along this closed loop, you can show that it's actually related to off-diagonal electrical conductivity. And this was shown along the low frequencies, and this is very fine. So off-diagonal conductivity is called anomalous off-diagonal conductivity because it doesn't require any magnetic field for it. So Hall coefficient is non-zero, even when there is no magnet. Okay, apply electric field, you get a current from that. Okay, so I'll now summarize whatever we learned so far. On the left-hand side is the geometric band theory, which I introduced to you in this last 20 minutes. And on the right-hand side is something you may have studied in textbooks already. So, consider now the geometric phase is like no bomb phase in quantum mechanics in the presence of electromagnetic fields. Very direction is like a vector potential classical electromagnetism. And very curvature is like magnetic field in a crystal, which is spread by electron. And Chern, this brings me to the next very important development in the last 20 years. Any insulator, you can calculate Chern, not for a metal, because for metal I showed you, you get off-diagonal conductivity. For an insulator, there is a gap, so there is no Fermi surface. All the states in the Riemann zone are occupied. So what you will say is, well, we can integrate around the boundary of the Riemann zone and calculate the Bailey phase transfer. And then what you get is actually the Chern number, which is a topologically independent. It differentiates objects of different topology. So if you have an insulator with Chern number 1 and you cut the surface out of it, you have vacuum on the right hand side or by the right hand side. Vacuum has the zero Chern because there is no electronic states there. That boundary surface has to be. So this is spectacular property of topological nature. And if you cut the surface of the insulator, you get metallic surface. And that metallic surface you cannot kill no matter what. And these are new types of insulators which you couldn't have guessed otherwise. You have to think of these ideas. So the quantum geometry that I introduced to you is also intimately linked to the topology of electronic structure in insulator. Okay. All this is very exciting, and you will say, how come we never saw this life? And the reason is that most materials you work with, let's say copper, silicon, and aluminum type crystals, they have two symmetries. One is time reversal symmetry, and one is inversion symmetry, spatial inversion. If a crystal has time reversal symmetry, very conventional is all function of A. If the system has inversion symmetry, it's an even function of wavelength. And as a result of all these solids, this very curvature analytically is zero. And that's why you may not have seen it. That's not a very good news because it means basically most materials which have this reverse. It means the quantum phase space-time of electrons in these insulators is flat. It won't show those exotic effects. Okay? So there came another development in field. It's called non-linear Hall effect. So the linear geometric effect I showed you is zero normally. And what they showed is this is a theory work which came up. That for linear Hall effect this condition is given, but what we say is if you apply electric field to the system, you break inversion symmetry by using a time field. And then second order you can start seeing these effects. That's all that. And cutting this technical detail short, what they show is you can have second order nonlinear Hall effect in the same way that I expressed, where the Hall current in y direction is proportional to square of electric field in this direction. And the proportionality constant here, V, is called Bailey curvature I. It's the first moment of Bailey curvature in physics. Yeah? That was the next development, and this was done by Soder and India with MIT. This is a theory work. And its verification came up next in a few years by Martin group in MIT. This is experimental work. And now let me explain this figure why nonlinear Hall effect is a beautiful thing to have. If you have a linear Hall effect on the left hand side, that comes up when Bailey curvature is uniformly constant. Yeah? But that's very rare. But if that is the case, you will see a linear Hall effect. Means applied frequency is omega and Hall frequency is also omega, but then the current has a very small angle with respect to applied direction of applied field, because typically these effects are weak. And you will say, well, if a current is slightly canted with respect to this direction, it may be hard to measure. But in the nonlinear Hall effect, you apply driving field along x direction and frequency omega, because it's second order effect. The Hall signal is rectification or 2 times omega, second order. Right? And as a result, Hall current is always perpendicular to the upward direction of light. And that is much easier to measure, even if the effect is weak, because the direction is perpendicular. So that's the reason this attracted Hall effect. Okay? That you will see, and then Bhuvaneshwari showed that in the material that Pablo was made, we could calculate Bailey curvature from first principles. I won't go into those details, that's a separate lecture by itself. But these are things which we can calculate from scratch without using any experience. You will see this is the distribution of Bailey curvature. Now this picture, by the way, is the quantum phase space of electrons in this constant, right? And you will see this is where the Bailey curvature is from zero. And as a result, electronic trajectory here will be suitable. And that's what gives rise to this interesting movie. So what Bhuvaneshwari gave up the student as a new idea is, look, if you restrict to static symmetries of crystals, we are still going to be very restricted in seeing such things. Like piezoelectric, which is a very important thing, right? Which is fundamental to your mobile phones, speakers, mic that you have. But those effects are seen only in crystals which are broken inversions. That's a relatively weaker condition. There are many crystals which are broken. But in this case, you end up having further. So what Bhuvaneshwari says is, can we not break symmetry dynamic? How do we do it? Let's say you create an oscillation in your crystal, then you break symmetry, right? You pull it around only one direction, crystal will lower its symmetry. Can we see these effects in that? That was the theory here. So our basic idea is you have this highly symmetric crystal that is If you vibrate, think about vibrations where the two atoms come closer to each other and farther from each other. You have, if you take a snapshot of this vibration, you get a structure where this bond is shorter and you break the three-fold symmetry of the piece. And when you do that, what you can show is you can induce a very curvature. Yeah? So a vibrational motion of atoms can lower the symmetry of the lattice as a function of time and create very curvature dipole which will also oscillate with time. And that should have an observable signature. That was the key idea. And that should this is what should be measured. So that's where we propose a new spectroscopy, which is based on the geometry of quantum structure. We call it GQS spectroscopy. And you will see now how it functions. So the idea is dynamical excitation. It doesn't have to be vibration. It can be a magnon, it can be other charge density, any excitation of a solid which lowers symmetry as long as this selection rule is satisfied. Derivative of very curvature dipole is non-zero. It will be an observable quantity. So it will have, of course, the normal prediction of second order effect. But these are our predictions that if this selection rule is satisfied, you will see additional peaks in the Hall signal. And those peaks will be like Raman signal, where vibration will be plus minus Stokes and anti-Stokes signal. Okay, how does this experiment work? You have a sample which you want to test this hypothesis on. You apply AC frequency, let's say half a beta frequency along this direction. Imagine a circuit, you can easily develop this. And what we say is you measure the current which is generated in bi-direction without applying any magnetic field. And you measure the current as a function of frequency. And what our prediction is, if the applied frequency is omega AC and vibrational frequency is omega naught, you will see these two additional three peaks in the spectrum. Yeah? So you don't need to use light, you can just use a circuit to measure vibrational frequency of the sample. That's the advantage here. Yeah? And similarly, you can also use emission spectroscopy. This is like Raman, where you shine light on your sample and measure the emitted radiation which is perpendicular polarized, which is like a Hall effect. And in that case, again, you will see peaks which are shown here. This is the rectification and second harmonical measure, which is possible only non-synchronicity system, whereas the additional peaks come in any system, and that's the prediction. Okay, so you can also use light scattering as a mode of operation for this. Alright? So evidence now you will say these are all theoretical ideas, but that's where when we don't do experiments, we do things, we show that it is possible. And that's when we show using first principles, this central telluride, which is the lower layer of two-dimensional tungsten telluride material, and we compress it along y direction and see what happens to the electron structure. As you compress it or tension to it, band structure oscillates. But from that you cannot tell that the quantum geometry is going to change. So what we are proposing is vibrations of lattice leads to oscillations in quantum. And that's what we show here. This is the leading curvature pattern, which is linearly proportional to the scale that you apply. And that means this selection will be satisfied. You predict them that it is what you should see in a real experiment if you carry out for instance. You apply electric field as a function of omega AC frequency and measure Hall current, and this is what you predict. By changing the applied frequency, you can change the Stokes and anti-Stokes states. So this gives you additional control in accessing the vibrational frequency. In Raman, you can change the frequency of light, but then all three peaks will shift from there. Whereas in our case, the central peak will remain fixed and the Stokes and anti-Stokes will be fixed. Okay, that's the advantage. You can also use it in a hybrid mode. You apply some electric current along its direction and measure the terahertz radiation, because some many times vibrations are in terahertz frequency. And by changing the AC frequency, you can modulate the signal in terahertz. And this opens up a new application. As you all know that terahertz frequency range is a forbidden electromagnetic range, meaning there are very few sources, detectors or manipulators available for optics in terahertz. And what we show is you can apply gigahertz frequency modulation and translate it to the terahertz frequency. Yeah? So this is a new sort of application that's possible. Of course, the intensities are going to be weak, but that we can work on by developing a suitable material to show such things. So the idea of this works very nicely based on that we introduce a new spectroscopy. However, there will be criticism that these ideas still apply to narrow band crystals, meaning very curvature is typically large only for crystals with very small band gap, where they are close to being held. Well, there are technical reasons for it. Basically, curvature is proportional to inverse band gap. So if band gap is small, then you should see these effects there. And then you say, well, most systems we look at, say, very young, we have band gap is too large. So what's the use? Yeah? Or boron nitride. So we show that we learn from the surface enhanced transfer, which is a well-established technique, and demonstrate that the similar ideas work in this context as well. So we say, if you have boron nitride, whose vibrational frequency you want to measure, you place it on top of graphene. Graphene is a very wonderful material, all of you know about it. It's a beautiful quantum material. By itself, it doesn't show these effects for certain reasons I can explain to you. But if you place boron nitride, vibrations in boron nitride can induce oscillations in quantum geometry of graphene. That's the concept. It's like a proximity effect, right? And those oscillations are shown here using our theoretical calculation. On the x-axis is u, which is the vibration of HDN, and on the y-axis is the very curvature dipole of graphene. And you will see it has the linear slope, linear behavior. So what they will predict is, if you can shine light with the frequency omega A and measure radiation scattered with a perpendicular polarization field, you will see behavior like this. That is, this is the omega 1 vibrational frequency, and there are two Stokes and anti-Stokes type of peaks that complete another 2 times frequency. Okay? So this is what we say that even for systems which don't have quantum geometry, now you can use GQS spectroscopy. And this is a new application of quantum materials in studying vibrational frequencies of other systems which are otherwise would exist. And we work these things in detail. This is the boron nitride which is vibrating, see, with respect to graphene, and that really changes the curvature of graphene, and that leads to the peaks that we predict here as a function of frequency. And these are relatively easy to measure. So we are hoping some experimentalists will be able to capture this prediction. So this is a little more realistic prediction that we have. This is constant telluride, semi-symmetric one. This is the GQS spectrum. I won't go through details, but you will see that if you apply shine light with the frequency omega L, this is 2 times omega A. And you see, if the Fibonacci frequency is less than 2 times omega A, you have peak here and peak here, which is separated by the same Stoke. And if omega frequency is greater than the frequency of light, like omega 3, then you have 2 peaks which are separated here and significantly separated. That separation is 2 times omega A, the frequency of light. So these weak spectra are predicted for a simple system, and this richness of the spectrum will make it even easier to interpret them, because you can control these peaks by changing the frequency of light. Okay, so that's the idea. To summarize, at least in some simple words, what we learned in this talk today is when an electromagnetic wave passes through a material, its propagation is determined by frequency-dependent dielectric constant. I'm sure any of you have seen it in advanced space. And that dielectric constant has 2 parts. One is the real part and one is the imaginary part. Imaginary part is given by actually the electrical conductivity frequency-dependent. Okay? When you do Raman spectroscopy, what you capitalize is the real part of this dielectric, generalized dielectric constant. In our work, we focus on the imaginary part, and more particularly the off-diagonal part, which is dependent on the Bailey curvature. And that's what is the consequence of quantum probability. Okay, so that's the basic idea. Here you can use light scattering to measure it. whereas here we have circuits as well as light scattering which we can do. More importantly, this spectroscopy that we propose captures relevant thermal and infrared all in one. The features are set of experiments, yes, Nanda has worked hard on these ideas. So what he did is he has a sample like this, and he has placed the sample on a piezoelectric substrate. Why? Because, see, the natural modes of vibration of the crystal typically are in very high frequency rates, they are or high. And those are harder to measure in circuits. Circuits are very difficult to do, about 10 gigahertz. So, what we decided to do is instead of looking at natural vibration, we guide the vibration. There we have control over the driving electric field as well as the vibrational frequency, which is up to you what frequency you want to do. So they vibrate the substrate, and as a result, the sample vibrates, and then they measure the Hall. Look what they find. Okay, so this was another beautiful thing about the interaction between theory and experience. We thought our theory was complete, and it would explain everything they did. But no, they found out some new features, which our theory didn't predict. Okay? And then we realized that our theory focused on the very early space, like this, where you have that conduction and balance dipoles, and they tilt during when you create an oscillation in the sample. But what experiments you want to do is, you not only tilt, but you also create the distance between these two poles to change. Oscillations are also possible in the location without changing the geometry. Okay? So these are all slow electric fields which are generated. That is not our new workflow idea. These are already this was predicted in 2010. So we have to use, we showed that we can use this as well as this and explain all the things. And more interestingly, what we show is the slow electric field can superimpose with the very curvature effect. So you have a coupling between them as well. So that's how the IFL experiments were very rewarding. They challenged us to go back to the drawing board and figure out that yes, pseudo fields and these are ours are emerging electromagnetic fields, gauge theory or gauge fields which come from the structural theory. So we have gauge type fields and pseudo electric fields, and they can add to each other in creating this. One remark for the students, these are not electric or magnetic fields you can sense outside. You have a sample and these fields are fed by the electrons in that sample. They are not fed by the outside world. Okay? So they don't escape the material that they want to be. Yeah? So that's the beauty and very interesting thing. But these are detailed experimental measurements that student who is a student of Nanda who did this experiment. These are all theory predictions by the way. And different here we are talking about voltage as a function of piezoelectric. This is the amplitude of oscillation, and that's here, linear proportional to the oscillation. Then this is Hall voltage as a function of frequency, and then also they basically the quadratic dependence here, and they also established basically linear dependence on the vibrational frequency. So all of the predictions that we have in the theory are at least qualitatively. We don't have matching between the intensities because our theory is the same classical theory. We don't fully mention that. So I'll summarize my talk here. We introduced the request vibrational spectroscopy, and we show that it can be used in transport mode, in the circuit mode, as well as light scattering mode, emission mode, and it can combine the capabilities of all of these. Secondly, it can be generalized to other dynamical excitations like plasma, whichever makes the symmetric dynamic. And lastly, these ideas are of course applicable to much wider sets of systems, including 3D materials, wide semi-metals, Dirac semi-metals. And those are more commonly possible, and we expect them to be quite rich in that. So this is the experimental work which is under review now. But we do have a partial verification experiment. So I acknowledge Bhuvaneshwari is the PhD student who wrote this work. Mandar and Surat and the group at the did experiments, which I showed in the last time. And Amit Randavan from Kanpur joined us in studying the theory. And I thank you for your attention, and I'll be happy to.
Any questions?
Okay. Yes. If you have it, we would love to work with you if you have the skills center. In fact, those are not commonly seen in India. I know Sri Ganesh in PIFR has some of that. But that's where these are the applicable. Okay. Sure. We'll be happy to can talk and plan.
The role of monolayer, because you are talking about monolayer, two layer. Go to four thicker or three dimension. What are these?
As I said, yeah, not only 3D, but it will be more richer. Because in 2 dimension, daily curvature is only along the direction which is perpendicular to the phantom plane. But in 3D, you can have in various directions. So, I have a few slides to show you if you want. So the next work with this, maybe Professor Satya will find it attractive. It's a new type of multi-phyloid we have to detect. And it's based on 3-dimensional superlattice of layered manganic oxide and layered manganic oxide. Okay? And this superlattice we show that has a very curvature dipole which can be switched with ferroelectric potential. You can switch ferroelectric dipole and you can switch to a very curvature dipole. So new type of features will be possible in 3D. So these ideas definitely apply. But we don't in the spectroscopy that I told you we have demonstrated it, but we are sure that they will be the more interesting opportunities.
Maybe more real aptitude when you go to.
I see. Okay, sure.
It is easy.
I understand. Thank you.
Yes. Very nice talk. Okay. If I am correctly know that you need to this very curvature diagram.
Yeah.
Right?
That's correct.
And that's everywhere there is strain applied.
Not necessarily.
So you need to come, so I was just thinking about the crystallographic aspect of this that.
So, for example, when there is a you imagine a sample sitting on a substrate. It's not frozen. You know, at any given it's oscillating it. Right? These are not natural vibrations.
Let's say it's experiment of Mandas.
Mandas is a driven vibration.
They have brought the accessible range to their.
No, they have brought it to easily measurable frequency range, which is a driven vibration, 50 to 5100 hertz. That's vibration. So that's a driven vibration. But the spectroscopy itself is for natural vibrations. And there you don't need any applied vibration.
No, but then the frequency is required an gigahertz, right?
But that's where your next colleague will be able to measure noise. See, levels also are easy to measure. Right? And more importantly, now, because become popular and commonplace until lesser scaling. Until then, it was purely academic interest type of a technique. But after that, the intensities were it became very common. So I agree with you at this stage it's at the infancy, but I do think it has a scope. Yeah. Okay. Yeah. Thickness which Mandali is 2 monolayers of graphene, twisted as well as untwisted. Both of them show these effects. Okay? As Sir pointed out, usually the larger intensities applied for thickness angles, which we need to work out though. I don't have a clear answer to offer you. So it should be the temperatures are low, temperatures below 3 K for Mandali's. At higher temperatures, some of these effects may wash away fluctuations in different levels.
Yeah, Rajiv. you can only make up 10 minutes. That's it. So it's a fantastic additional structure this stuff. And that can also lead to training this. But then what we are starting
Look. Okay. Okay, let me explain. Take an example of a ferroelectric plate. Right? It has polarization, it is non-zero, and that is very fixed. Got it? I explained that was an important development in 1992. Now you induce a vibration in a ferroelectric plate. Do you think polarization will oscillate or? It does. In fact, that's how you measure IR. You measure in IR spectroscopy. The coupling between electromagnetic wave and magnetic is called Baum effective charge, and that's similar to what I discussed here. There also the Berry phase will oscillate. Berry phase, which is calculated along a closed loop, will oscillate if you change the structure of the oscillation. So indeed, the vibration doesn't have to close the loop. It will be great if you tap, and then it will need to charge pumps. You can count the charge from one inch.
Sunday.
very insightful. One clarification. I was trying to understand. So we are starting with the like symmetric distance, like central symmetric distance.
Yes.
And that was giving some sort of vibration.
Not giving vibrations exist in the lights.
And because of that, locally it is breaking the symmetry. And because of that,
Not locally, dynamically. Locally tight. Not instantly.
because of that, you are having some very temperature
Oscillations.
oscillations.
In
And
that.
then you are getting some signal.
That has a Hall signature.
That was a pulse.
Yeah.
But I think this kind of things are already reported on this content identified or NOC.
The ordinary nonlinear Hall is reported. That's the MIT experiment I showed in 2019.
Like pump pro.
Yeah.
Like shooting like very intense pulse of light. And then locally you can basically break the symmetry. And then you have the consistency of answer.
Sure.
Right. So then you will see the connection points, then open up or close.
Right.
So I was trying to understand, is it the same thing?
See, the pump probe doesn't involve geometric curvature ideas. That's the difference. You are right. In spirit, they are very similar to the experiment you are in research. But in this case, the vibration does not just change the energy values of structure, but it creates changes in the geometric curvature of it.
Very
You don't need intense pulse. No. That's the idea. Vibration is what is inducing this oscillation. Yeah, that's why you will work at low temperature, I explained, but they don't have to be high amplitude or height doesn't have to be exorbitant.
It just probe.
Yeah, but you are right that what you do in pulse to pump probe experiments are very similar in spirit, but not geometry. That's the key.
Like, I was just trying to understand the formula you gave for any curvature.
Yeah.
So it is connected with very connection.
Right.
And there was some imaginary number I.
Yeah.
So I was wondering, like, why do you need this imaginary?
Okay, it's very simple, right? So any phase factor of the wave function is e raised to I phi. So if you want to pull out that phi, what you would do is you take a water from. But then to get rid of I, to recover only phi, you have to multiply phi.
So we could imagine the very connection.
Very curvature, you can write, okay. So you imagine a complex number z. You can always write a complex number as rho times e raised to I theta. And what we are interested in is not rho, we are interested in theta. So you take logarithm and take imaginary part. And this is actually, this is a good question, when it applies to any two vectors. They don't have to be involved adiabatically. And in fact, the mathematics of it was also developed in the differential number based on the
Okay.
differential probabilities.
Dr. Pan.
Very nice job. Yes. Nice side. I was wondering why you not architect of
No, it linearly is proportional, yeah.
the high temperature to increase.
Yeah, but the randomness may kill some of the, it will wash out the effects. If the wind decay time becomes longer, then it may not be easy. So to see those peaks, you may work at home. We haven't really worked on temperature dependent full quantum theory, but it's always safer to work at, but you're right that if you increase temperature, amplitude will go. No, because we don't know it possible. Okay. That's the good thing.
So can we define this as caused by thermal disorder?
I would say not disorder, thermal breaking loss symmetry, or dynamically broken state.
Professor Raichowdhury wants to ask one question.
Hey, Umesh, from Kolkata.
Hi, Arun, good to hear you.
Yeah, okay. I have a very simple question. Essentially it is a nonlinear coupling of phonon field with the Berry-Carpenter dipole, if I understand it correctly, the core of the problem.
Okay. Yeah, I don't think, Arun, I could hear you, sorry.
Yeah, go.
Can you repeat your question, please?
Yeah, the question is that, if I understand it correctly, the core of the problem is the nonlinear coupling of phonon field with the Berry-Carpenter dipole.
No. Okay. So the coupling between phonon and Berry-Carpenter dipole is linear.
Okay, that part is linear. Okay, now the related question is that if I am able to do very low frequency, low temperature thermal conductivity type of experiment, should I be seeing the signature of this mode?
Yeah, I guess it will be thermal Hall effect, and people are thinking about it, but that's a different mechanism, I feel. We haven't worked it out, our theory doesn't really predict that. Yeah.
Okay, thank you.
If it is electronic thermal conduction, it should see these effects.
Okay.
If it's phonon plus thermal conduction, which will I guess will be low.
Okay.
Thank you. It's a good question. It stimulates me to think further.
Okay.
Thank you.
I think we can close this session over here. Thank you very much.
Thank you all for your interest.
I request now and Director Moderator to propose vote of thanks. Before that, I request our Director to give memento to both our guest of honor and to Chief Guest.
Thank you, Dr. Satya. I have been given the responsibility of proposing the vote of thanks. Before I formally propose the vote of thanks, I just like to thank Professor Varma. He given an excellent talk. And many people nowadays hear daily curvature, geometric phase, and all these things, especially students, those who are new, are highly confused on what it is. I think after today's talk,
I think everybody understands what is a berry phase and geometric phase. You demonstrate using a simple handheld vector model. I know everybody. Sir, thank you very much. And so today's proposal, in the vote of thanks, first I would like to thank Professor Valmare, President James CSR, to have agreed to our invitation and come here and deliver the talk, especially considering the present scenario of where the aviation distribution with the Indigo and all that. He has changed, I understand he has changed the flight to India and then came all the way and delivered this talk. And thank you very much and an excellent talk. We really appreciate your efforts and the talk and all that thing. Thank you on behalf of the consortium. And the next is we also thank Professor Rakesh Shingai, the Vice Chancellor of Vivekananda University, to find some time from his busy schedule and come here and give his address and grace this occasion. And we thank you very much, sir. And we also keep in your mind and in our program that whatever suggestions that you have given, we will try to incorporate. And we also actually, on behalf of the consortium as a whole, especially Indo, we are, I think, receiving continuous support from the DAE, which you represent, and various infrastructure and other facilities. I hope we still want more help. I think Professor Satya has told already. We require your help and cooperation in future also. Thank you very much, and I hope you will get the cooperation and support that you have been extended. And we also thank in this occasion, various our dignitaries, senior colleagues from RRCAT, IIT Indore, our own consortium, and ex-colleagues, some of our ex-colleagues have come. All the way they come to attend this annual day, and our students and other people. Many of our consortium faculty and students have worked behind to make this event possible. And we thank all of them for not only doing all the background work and also attending this and make this event successful. Thank you very much. And in the last, I would like to thank actually our director and Dr. Vasant Sate. This annual day which we have been celebrating for some reason during COVID, it got stopped. Okay, and we have not had an annual day celebration, I think, now for 5 years, I guess. So they understood, the consortium people think this is like a festival, consortium festival. So that way the director and I think Satya also promoted this idea that we should have this annual day celebration. And so he thanked both of them to restarting this annual day celebration, and also on behalf of the consortium people, community of the consortium, I thank both them. Thank you very much.
Thank you all. Please join outside for IT. Honoring.
My laptop, I will send it to your office.
Thank you.